Hello, welcome to the second session of Scalable Machine Learning. After the introduction to Spark and HPC in the first week, this week we are going to go deeper to see how Spark works. So let me share the screen with you. So in this second lecture, we will study RDD, data frame, and machine learning pipelines, and parallelization. So these are the four topics, that is resilient, distributed data sets, and second, data frames and data sets, and third, machine learning pipelines, and finally, execution parallelization. We will look at the RDD first. RDD refers to resilient distributed data sets. So this is a distributed memory abstraction. It enables in-memory computation on large clusters in a fault-tolerant manner. And it is the primary data abstraction in Spark, and it enables operations on collection of elements in parallel. And the three words RDD, the first R means to recompute missing partitions due to node failure. That means this RDD can recompute the missing partitions if one or some of the nodes fails in a cluster. And the second word, distributed, means the data are distributed on multiple nodes in a cluster. And finally, data sets means the data are basically a collection of partitioned elements. So they are data sets. So this is a simple illustration of RDD where the data is partitioned into several partitions, and then they will distribute it to multiple workers. And there are several characteristics of RDD. The first one and most important one is in-memory computation. And in the design of RDD, the principle is to keep data inside of RDD to be stored in memory as much as possible and as long as possible. And secondly, RDDs are immutable. That means they are read-only, and they will not change after creation. And they will only be transformed using transformations to new RDDs. And thirdly, RDDs are lazily evaluated. That means RDD data are not available or transformed until an action is executed. Only an action will trigger the execution. And fourth, RDD process data in parallel. And fifth, the data in an RDD is partitioned. And then these partitions are distributed across nodes in a cluster. And finally, RDDs are cacheable. What this means is the RDDs can hold all the data in a persistent storage, such as memory or disk. We will look at this in more detail later. To understand why RDD want to keep the data in memory as much as possible and as long as possible, you need to understand the computer memory hierarchy. So computer memories are organized in this hierarchy. At the top are the CPU registers, right? So they are the CPU memory. These are the fastest, and they are also most expensive, right? So therefore, they are typically very small, right? Very small. And the next level is a cache memory, right? So usually they have cache 1, cache 2. They are a bit cheaper than the CPU register, but they are also slower, right? So then moving down are the RAMs, right? So that's if when we buy a computer, you look at the RAM, right? The memory, we are talking about the main memory over here, right? So they are the RAMs. And they will be even slower and even cheaper per bit. And then move downwards, then that will be the magnetic disk, that will be the disk storage, including your SSD. And then moving further down is the optical disk, such as DVD or compact disc. And at the bottom is a magnetic tape. They are the cheapest per bit, but they are also the slowest, right? So if your data is stored at the bottom, and if you want to access from the CPU, it will be very slow. Therefore, the higher your data is in this hierarchy, the faster your processing will be, right? So that's why in Spark, the RDD want to keep the data in the main memory as much as possible and as long as possible. There are two primary RDD operations. The first one is transformation. Transformation takes an RDD and returns a new RDD. But in transformation, nothing gets evaluated or computed, right? So transformations basically take an RDD and return an RDD, right? So it will take an RDD and return an RDD. So that is transformation. So there's no computation over here. It is just encode how the data will be transformed. And the second kind of operation is called action, right? So it's called action. So in action, all the data processing queries are computed or evaluated, and the result value is returned, right? So therefore, action will take an RDD and return a value, right? So that is what we want to compute. So that is action, right? So action. So for transformation is RDD in, RDD out. And for action is RDD in and value out, right? So basically what we want to compute is the output. So when we work with RDD, there's a very standard workflow. The first step is to create an RDD from a data source, right? From either RDD or from file. And then the next step is to apply some transformations to that RDD. And after the transformations, we will need to apply actions to an RDD. And in this workflow, as users, we can control the persistence of the data, and we can also control the partitioning of the data. So here is an example, right? So for example, here is a Python list, and through a parallelize operation, we create several RDDs. And then we apply transformations, filter, and map. And then after that, we apply an action called collect, right? So this collect will produce a result, right? So only the collect action will cause these transformations actually be executed. So there are three ways to create RDDs. The first one is, as shown in the example earlier, is to parallelize existing Python collections, or for example, a list. The second way is to transform existing RDDs, right? So from RDDs. And the third way is to create from external files, such as text files or Hadoop files. And for these operations, we use the Spark context SC APIs, such as sc.parallelize, SC Hadoop file, and SC text file. Right? So SC Spark context is for RDD, for us to create RDDs. So let us look at a little bit more about the Spark transformations, right? You can click this link and go to the documentation. So Spark transformations basically will create new data sets from an existing one. And just remember, right? So it will be a lazy evaluation. So transformations, we just remember the transformations applied to the base data set, but the results are not computed, right? So they are not computed. And Spark can optimize the required calculation. And this will also enable Spark to recover from failures. And if you go to click this link and go to the documentation, you will find the list of commonly used transformations and what it means, right? So for example, map, filter, flat map, and map partitions, right? So, and the second kind of operations, action. So actually that is action causes Spark to execute the recipe to transform the source data. And this is a mechanism for getting results out of the Spark. And if you click this link, you will see the documentation list of several actions, right? Commonly used actions. For example, collect. We often use this one, and count, right? So we have used count. So those are very commonly used actions. So let us look at another example. And this example is from the Spark paper. Right? So that paper from UC Berkeley, published in 2012, right? So that almost, it was invented 10 years ago, right? So here is a figure in the paper, and this is called lineage graph, right? So it's called lineage graph. And here is the corresponding code in Scala, right? So Spark originally was in Scala, right? So this is a code in Scala. It is very readable, so don't worry, you don't need to actually learn the Scala, but you can just read it and you will roughly know what it is doing, right? So what it is doing. So for example, here it starts with a base RDD, which is created from a text file, which is you get it from the Hadoop file system. And then through a transformation filter, we obtain a transformed RDD, right? So that is the errors. And because we intend to reuse it, so we do a persist, right? So we do a persistence. Or you can also do cache, right? So after that, we do an error.count, right? So this is an action, and this will trigger the previous transformations to be executed. And after that, we can do another transformation and action, right? So another operation. So in this example, the scenario is that the web service is experiencing some errors, and the operators want to search terabytes of logs in the Hadoop file system to find the cause of such errors, right? So for example, this is looking for the errors, and then it will look for the HDFS type errors, right? So therefore, line 1 here create the RDD from an HDFS file, but the file is not loaded in memory, right? So because this is a transformation. And line 3 asks the errors to persist in memory, that is to be cached in memory, right? So that is not actually loading the data and keep it in the memory. This is just to a plan, right? So this is only thing that when the data is loaded, it should be cached in the memory, right? So but only when you do count, it will actually do the loading, right, and the caching. So this lineage graph facilitates fault tolerance, right? So because RDDs keep track of the lineage, and it will have the knowledge of how the RDD was derived from and to compute its partitions from the data in stable storage, right? That is, this lineage will tells the program how every RDD is derived from some stable storage, right? Stable storage, so that it will be able to compute its partitions always, right? So, and in the case that a partition of errors, right? So for example, in this example, right, a partition of the errors is lost, right? In this example, the RDD is the errors, right? So if one partition of the errors is lost, then what the program will do is to rebuild it, right? We'll rebuild it by applying a filter on only the corresponding partition of lines, right? It will only apply the filter to the corresponding partition. And then these partitions will be recomputed in parallel on different nodes, right? So because that node, for example, fails, right? So the node failure, then we can recompute that partition in parallel on different nodes, right? So without rolling back the whole program, right? So this is the whole purpose, right? So when one of the node fails, we do not want to redo everything, right? So because just one, for example, if there are 100 nodes, right? If just one node fails, we don't need to redo all the computations, right? So if that is on our personal computer, right? So if there's an error, you have to rerun your program, right? So but in Spark, when you run it on a cluster, if one node fails, you just need to recompute and redo that part, right? That partition. So that is how this Spark achieves fault tolerance, right? So here is again the previous example, right? So this is, they are starting with RDD, right? So from the lines to the errors RDD, and then to HDFS errors, and then to the time field, right? So here the program, it assumes the time is a field number 3, right? So in the tab separated format. So let us look at the operations step by step, right? So the first step, RDD, right? So it basically this defines the base RDD, right? So, and then this errors equals to lines dot filter. This is the transformation will result in a transformed RDD, which is errors, and we persist the errors, right? So that is to cache it, right? So this is from RDD to a transformation and returns another RDD. And the next error count, that is an action, right? So that is an action, and this counts will cause a Spark to read the data, right? So from this address, I read the data from this address, and will also sum within the partitions, and then combine the sums in the driver, right? So this action will cause the following executions, right? So, and we can also put transform and action together, right? As this line shows, you can write all this as one line, right? So very compact. So RDD persistence is a very important concept for the efficiency of Spark, right? So the nodes will stock partitions for reuse, right? So reuse in other actions on that data set, right? So we will basically store those reusable partitions, those partitions that will be reused. And in persistence, the storage levels can be set by the user for each persisted RDD. And the memory-only option is the default, right? So the memory-only option is the default. That means we will only cache, right? We will only keep the data in the main memory. Another option is memory and disk. And this is to say, if the data is too large for the memory, then it will store the remaining partitions on disk, right? So in either cases, right? So if there are still some partitions cannot be fit in, then they need to be recomputed when needed, right? When needed. Cache, right? So we have seen this method in the first lecture. Cache means the default option, right? So basically, cache means to persist with a storage level of memory only, right? So here is a nice illustration, right? So when you have a memory only, your partition will be stored in the memory, right? So when you have a memory and disk, right? So if you want to persist memory and disk, then your partition will be stored in, kept in both memory and disk. So why we want to persist RDD, right? So as we mentioned earlier, that is because of this hierarchy of computer memory. So if the error will, if we will do another action on the errors, I see here we persist the error. If we will do the count again for another type of task, then if without persistence, we have to load the data from the bottom of the hierarchies and then do the recomputation, right? So that will be slow, right? So that will be slow because when you have to load the data from a lower tier, that slow your computation down, right? So you will, it will be slower, right? So the persist basically will cache the data in the memory, right? So this will reduce the data loading cost for further actions on the same data, right? So that is when we want to do persist, we expect there will be further actions on the same data, right? If there's no further action, then there's no need for you to persist, right? So to cache the data. And again, right? So the persist is not an action, right? So persist is more a transformation than action, right? So it do nothing, right? So this one is not doing anything, right? So it is just to define the transformations. It is a lazy operation. It just tells the program, read this file and then cache the contents, right? So when the action is triggered, right? So when an action is triggered, then the program will do the computation and do the data caching. And another point is that Spark also supports the key value pairs, right? Key value pairs. For example, these transformations are designed for the key value pairs data, right? So data sets of the format of key and value. So that is a detailed introduction to the RDD. And in the next section, we will talk about data frames and data sets.